Hello, this is Dr. Alemi with a lecture on paired t-test or paired z-test. Recall from the framework of hypothesis testing that we introduced in the last lecture that there are several steps. First, we examine the assumptions, then state the hypothesis, calculate the statistic, look up the p-value, and then decide to reject or fail to reject the null hypothesis. In this set of slides, we apply the framework to conducting paired tests. Two sets of observations are paired if each observation in one set has a special correspondence or connection with exactly one observation in the other set. The two observations share the same characteristics but are different in the variable under study. To analyze paired data, it is often useful to look at the differences in outcomes of each pair of observations. When analyzing data from electronic health records, managers match cases in the sample to controls. They do so in order to make sure that the treatment effect examined is only seen in the cases and not in the controls. Every case is matched to controls on all relevant characteristics. Cases have received the treatment or treatment intervention, and controls have not. In this fashion, matched case controls allow one to estimate the effect of the treatment intervention, controlling for differences in patient characteristics. A matched case control is analyzed using paired observations. Here are some examples of pair comparisons. One variable is measured on two occasions where the occasions share key characteristics. First step is to check assumptions. So our first assumption is that the data are paired with each other, that in all relevant characteristics the two observations are the same, except for the variable that's being measured. The second assumption is that the differences of pairs of observations are independent. The third assumption is that the average of the differences has a near normal distribution. This assumption is verified when we have more than 30 cases in the sample and when the distribution is not very skewed. If we have less than 30 cases, we still may be able to do paired t-test using the t-distribution instead of the normal distribution. In our framework for hypothesis testing, the next step is to state the hypothesis. The null hypothesis is the mean of the differences is 0. The alternative hypothesis, if we are doing a two-sided test, is that the mean of the differences are not the same. If doing a one-sided test, the alternative hypothesis is that the mean of the differences is higher than 0 or lower than 0. The third step in our framework for hypothesis testing is to calculate the statistic. The statistic z is calculated from average of the paired differences in the sample divided by the standard error of the differences. When the sample size is smaller than 30, instead of the normal distribution, we use the student t distribution. The student t distribution has a lower peak and a higher percent of observations fall in the tails. The next step in our inference framework is to look up the p-value associated with a calculated z or t statistic. The last step in our framework is to infer from the sample if the population has the hypothesized null value. Let's look at an example. Suppose we want to know that hospitals that predominantly serve minority populations are priced differently than hospitals that do not do so. In each city, we have looked at the prices for a day of hospitalization at two hospitals, one that serves minority populations and another that does not. The differences of these two hospitals for 73 cities are reported here. First, we check assumptions. The assumption that hospitals are paired may be reasonable, as we have selected the two hospitals to be in the same city. The assumption of independence may be met if we sample less than 10% of the available cities, or if we randomly choose which city to examine. The assumption of near normal is met because the sample size exceeds 30, and if the data are not highly skewed, then the normal distribution can be assumed. A histogram of the data could establish if the data are skewed or not. Next, we state the hypothesis. The null hypothesis in this case is that there are no differences in the two types of hospitals. The alternative hypothesis is that there is a difference. We now calculate the statistic. First, we calculate the standard error of the mean of the differences. The problem gives us the standard deviation of the differences and the sample size. From these two values, we calculate the standard error to be 1.67. The z-statistic is calculated as the ratio of the average of the differences by the standard error. In this case, the z is 7.59. We now look up the p-value associated with a z of 7.59. This z-score is so large that it isn't even in the table, which ensures that a single-tailed area will be about 2 in 10,000 or smaller. Since the p-value corresponds to both tails in this case, and the normal distribution is symmetric, the p-value can be estimated as twice the one-tailed area, so 4 in 10,000. Last step in our framework is to infer from the sample if the population has hypothesized null value. The null hypothesis is rejected. We have found convincing evidence that the two types of hospitals do not have the same price. In this lecture, we have used our inference framework to see how to compare several matched observations.